Hey everyone, Moisa here. This is the first video of a two-part series on the steady-state response of a system driven by a time-varying sinusoidal source. The objective is to make the behavior of power systems intuitive and easy to understand. The approach will be visually rich to help get at the heart of the matter. Part 1 focuses on the steady-state response in the time domain, while Part 2 transitions the response to the frequency domain. A link to Part 2 will be included in the description box. By the end of this series, we should have a solid grasp on the behavioral response of a continuous time linear system. Additionally, we should understand the motivation for performing steady-state analysis in the frequency domain, circumventing the need to solve differential equations in the time domain. This effectively reduces our workload to the algebra of complex numbers. As the video title suggests, we are highlighting the steady-state response. With that objective in mind, after establishing its validity, we will discard the exponentially decaying transient component. The attention we're putting on the steady-state response is rooted in the reality that power systems operate at near steady-state conditions. Let's get started. When a system is excited or driven by a time-varying sinusoidal source, naturally, we would like to know, what is the system's response? How does it behave? For example, what kind of current does the system draw, and what is the relation between the system's response to the excitation source and the source itself? Before we analyze the response of the system, it's critical to have a firm understanding of the source. This stems from the fact that in linear systems, the response is a scaled and shifted replica of the source. Therefore, in analyzing the source, we are most of the way there in understanding and quantifying the response. We will discuss linearity and the importance of linear systems in another video, which I will include in the description box. For now, every system that we discuss is assumed to be linear. Consider a series RL system comprised of a switch, an ideal resistor, an ideal inductor, and a time-varying sinusoidal voltage source V of t. Let's define what it means for the voltage source to be time-varying and sinusoidal. Time-varying indicates that the magnitude or strength of the source is not constant, but rather fluctuates or varies with time. It is a property specifically associated with the strength of a signal considered over a period of time. As time elapses, the strength of the signal changes. Therefore, by definition, its strength is a function of time. The fluctuating strength of the signal is quantified mathematically by the trigonometric sine function, hence where the term sinusoidal comes from. Notice that a change in the quantity of elapsed time generates a corresponding change in the strength of the signal. Let's explore the sinusoid's functional dependence on time. From the previous illustration and from its very notation, we can clearly see that time is the input to some function v of t. In turn, the function operates on its input to generate a corresponding output. The process repeats itself for every instance of the input. This functional input-to-output operation generates a set of input-output value pairs. If we consider the set of all value pairs and plot them, we get a waveform that is continuous in time and sinusoidal in nature. Note, v of t is simply a function that takes time as an input and maps that input to a sinusoidal output. At this point, we should be asking ourselves, how can a function map an input as ubiquitous as time to a sinusoidal output? To that end, we need to closely look at the mathematical definition of the function v of t. We begin with the coefficient of time, omega. Omega represents angular frequency and is defined as the angular displacement per unit time. It is equal to 2 pi f, or equivalently 2 pi divided by the period, and carries units of radians per second. At the moment we begin to measure time as indicated by the timer, the argument of the sine function begins to advance from its initial position of 0 pi radians. After 4 seconds have elapsed, the argument has advanced to a position of 8 pi radians. This change in angular position or value from 0 pi radians to 8 pi radians is by definition the angular displacement, and when taken with respect to the corresponding change in time, evaluates to angular frequency omega. In short, omega is the rate at which the argument of the sine function advances or gets displaced. Next is the product of angular frequency and time, denoted omega t. We defined omega as the rate of angular displacement. Therefore, the product of omega and t reduces to angular displacement. Let's look at a couple of examples. If omega has the value of 2 pi radians per second, then after 1 second, the argument has been displaced a total of 2 pi radians from its initial value. If omega remains the same, but the time considered is now 2 seconds, the argument has been displaced a total of 4 pi radians. In essence, omega t dictates the travel or displacement of the argument as time elapses. The last variable in the argument of the sine function is the phase angle theta, which is also called the zero offset. The zero offset, as its name suggests, determines the instantaneous magnitude offset from the sine function's zero-time reference value, that is, v of t evaluated at t equals 0. Notice that when t equals 0, the argument of the sine function reduces to the phase angle theta. The sine function then operates on theta to procure its zero-time instantaneous magnitude. We've defined every variable in the argument of the sine function. Let's look at the sine function itself. To begin, we've set the period of the function to 12 seconds, which necessitates an angular frequency of pi over 6 radians per second. The zero offset phase angle theta has been set to 0. The omega t displacement axis is being introduced for reference purposes only, to exhibit the full effect of time on the argument of the sine function. Recall, time is the input to the function. At the moment we begin to measure time, that is, at t equals to 0, the argument of the sine function evaluates to 0, and the sine of 0 is 0, confirming this function has no zero offset. After 1 second of time has elapsed, the argument has advanced or been displaced a total of pi over 6 radians, as indicated by the omega t reference axis. In turn, the sine function operates on its argument to generate the output value of 0.5. After 2 seconds of time have elapsed, the argument of the sine function has advanced a total of pi over 3 radians. The sine of pi over 3 evaluates to 0.86. While time continues to elapse, the process continues to repeat itself. Notice that the points on the graph correspond to discrete moments in time that we selected as part of the narrative. In reality, there are an infinite number of discrete time values between any 2 points. In turn, the sine function operates on every instance of its argument to generate the segment connecting the points. That is all to say, the points were not arbitrarily connected, but rather with intention. The last element in this function is the coefficient v sub m. V sub m is referred to as the amplitude and acts to scale the function by either stretching or compressing the sinusoid vertically. The amplitude is the maximum instantaneous magnitude of the waveform, hence sub m for maximum. Let's conclude our analysis of the source with a parallel. We can visualize the input, which we've identified as time, as the fuel that the omega t engine consumes to power the argument of the sine function to advance and pass through all its possible values. In turn, the sine function operates on the complete range of its argument, generating a continuous time sinusoid. Thus, the functional relationship between the time input and the sinusoidal output has been defined for the source. Now that we've completed our analysis of the source, and keeping top of mind that we're dealing with a linear system, let's look at the response when the system is being excited by the source. Revisiting our series RL system, we want to affirm that time starts at the moment the switch is closed. The goal is to calculate the current response after the switch has been closed, that is, I of t when t is greater than or equal to 0. We begin with direct application of Kirchhoff's voltage law, which states that the algebraic sum of all voltages in a closed loop is 0. This generates a first-order differential equation. We rearrange the equation by isolating the voltage source. Next, we divide both sides by L to put the differential equation into standard form. This enables us to identify the functions p of x and q of x. To solve the differential equation, we need to identify the factor of integration I of x. We can now express the general solution. Substituting the values we identified for I of x and q of x, produces a solution that contains the integral of the product of two functions. To evaluate further and dispose of the integral, we have to apply integration by parts 2 times and the sign of the sum of two angles trig identity. We now have the current response of the series RL system. This response has a rather intimidating form, but if we take a closer look and use a graphical approach, it becomes easier to digest. We begin with the first term. The coefficient of the first term does not possess a t variable. Therefore, it has no functional dependence on t and simply evaluates to a constant, which we're going to represent with the letter k. This reduces the first term to the product of k and the exponential function. Plotting this term reveals an exponentially decaying graph. The intercept of this graph is k, since at t equals 0, the exponential component reduces to 1. This term is referred to as the transient component because it is temporal in nature. It approaches 0 as time elapses and therefore is irrelevant to the system response after a very short period of time. Next is the second term. The coefficient of the second term also does not possess a t variable. Therefore, it evaluates to the constant b, to distinguish it from the constant associated with the first term. The second term reduces to the product of b and the sine function. The graph of this term is a sinusoid. The intercept is a product of b and the sine of theta minus beta, since at t equals 0, the argument of the function reduces to theta minus beta. This term is referred to as the steady state component because it persists as time elapses. If we now consider the total current response, which is the algebraic sum of the transient and steady state components, we get a sinusoidal waveform that has an offset equal to the magnitude of the transient component. The offset levels off and becomes negligible as the transient component approaches 0. In other words, the total response becomes the steady state response as the transient component decays. For this particular system, the total response equates to the steady state response after about the first cycle mark, which corresponds with the transient component becoming infinitesimal. Since we are highlighting the steady state response, we will discard the transient component and as a result, the total system response for the rest of this series. Let's plot the sinusoidal voltage source and the steady state current response on the same plane to get a visual of the relation between them. Notice that the current response is a scaled down and shifted to the right replica of the voltage source. In other words, the system is drawing a sinusoidal response that operates at the same frequency as the sinusoidal source driving the system. This is an artifact of linear systems, which we will discuss in depth in another video. This reality is further confirmed if we look at the mathematical expressions for the steady state current response, I of t, and the sinusoidal voltage source, V of t. Both expressions possess the same angular frequency omega. Therefore, they operate at the same sinusoidal frequency as given by f equals to omega divided by 2 pi. Furthermore, the amplitude of I of t is equal to the amplitude of V of t divided by the magnitude of the series RL system impedance. Therefore, I of t is a scaled down version of V of t. Lastly, the argument of I of t is displaced by beta with respect to the argument of V of t, which acts to shift I of t to the right. The phase displacement between the sinusoidal voltage source and the steady-state current response represented by beta can be expressed in either radians or degrees. Since we're in the time domain as indicated by the time axis, it is good practice to convert beta to its corresponding delay in time. Recall that the angular displacement, also referred to as the phase displacement, is represented by omega t. Consequently, for a phase displacement of beta, the corresponding time delay in seconds is equal to beta divided by omega. This concludes part 1 of this series on the steady-state response of a linear system in the time domain. In particular, note that in our quest to acquire the system's current response, we had to solve a first-order differential equation by leveraging integral calculus and manipulating trig functions, which is mathematically time-consuming. In part 2 of the series, we will develop a technique for transitioning the steady-state response to the frequency domain, circumventing the need to solve differential equations in the time domain, which reduces our workload to the algebra of complex numbers. I'll see you guys next time.